security.
Yeah, thank you, Alessia. First I will present a bit, very briefly, the company. Micron is a world leader in semiconductor memory. So it produces DRAM, flash memories for all sorts of different markets, from the automotive to the mobile to the data center compute market. I work in the Vimercate site in Italy, where there is a strong legacy of knowledge in manufacturing, especially storage class memory, so emerging memory. So today I'm gonna talk about Cxl, which is basically a new class of interconnect, a new communication protocol, which stems from the need of a faster and more flexible interconnection technology between a data center server or a data center rack, so a collection of server, and some peripherals, which might be accelerators. In fact, the growing need of, for example, machine learning tasks in data center usage requires a more efficient way of moving data between the host and the peripherals. In particular, Cxl is actually it's right now still in development, but is backed by many big players in the data center market, and also by manufacturers of memory like Micron. So what is Cxl? Cxl basically it's a memory coherent, so able to guarantee basically a synchronization between the caches of a device and the host. It's a high speed because it's able to reach a full duplex bandwidth of 64 gigabytes per second, 32 per each side, and it's built on the PCIe Express 5.0 PHY. So it builds on an already established electrical medium, so that we can leverage the sum of the existing infrastructure for forward compatibility. There are now 3 established types of Cxl devices. The type 1 are cache coherent accelerators, so accelerators which instead of moving data back and forward using a long burst of DMA type, such as existing PCI Express peripherals, instead they transfer data in very small chunks of 64 bytes, and this data is kept, the caches on the host and the peripherals are kept coherent. We have then the type 2 devices, which also contain some kind of managed memory inside the accelerator itself, so that software can be optimized to move data which needs to be processed by the peripheral near the peripheral, so that then it can be accessed in a faster way, in a more efficient way. And finally, there is a third kind of devices, which is the kind which interests Micron the most, because it's the main memory expansion kind of devices, which are a way to expand basically the main memory of a host, but instead of mounting the DIMM sticks inside the machine itself, thanks to the Cxl interface, they can be mounted outside the server, so that this leads to a greater improvement in flexibility and manageability. So we will focus on Cxl Type 3 external main memory expansion drives. In this slide, you can see an example of the form factor that could be used by future Cxl-based memory devices. So it's main memory, but it uses the form factor which is traditionally used by SSD drives. So we're talking about the security of CXL. So let's begin from threat definition of CXL. So what are we defending against? What is at risk in a CXL type 3 peripheral? Given the fact that the CXL peripherals can be externally mounted, therefore they can be accessible outside of the device. Thus, to access them, we are not protected by tamper switches of the sort, so they can be subject fundamentally to physical attacks, which is something that usually DIMM sticks are not subject to because they are mounted inside the host machine. Therefore, an attacker with physical access to the device will try to, for example, violate the confidentiality of the data, which is transferred between the host and the memory, either by directly trying to sniff the protocol transaction or trying to impersonate a legitimate device and thus receiving the confidential data which should not be entitled to receive. Another potential threat might be the violation of the integrity of the data. For example, an attacker might try to electrically put an interposer between the host and the device and to perform the so-called man-in-the-middle attack. So modifying the data in transit in the protocol with the objective of causing, for example, a privilege escalation attack on the host or any kind of memory corruption in the host itself. Since this is main memory, it's ultimately trusted by the host, which believes that whatever it accesses it wasn't changed by any other malicious actor outside of the host itself. Finally, another threat could be the replay of a memory transaction. And we have to take particular care even to this kind of threat, because even if an attacker is not able to violate the other two properties, the confidentiality and the integrity, the fact that an attacker is able to replay a valid transition which happened in the past is dangerous by itself. In fact, it can lead to a rollback of the system to an insecure state, or in general to memory corruption. And when memory is corrupted, a vulnerable, a buggy software can basically, in the end, be exploited and can lead to either user data exfiltration or privilege escalation. So how are these threats basically coped with in the CXL protocol? This protocol has luckily a built-in protection against the three threats that I've listed, which is called the CXL IDE, or Integrity and Data Encryption, which is a specification which is derived from the similar feature with identical name present in the PCIe standard, which basically it's link level encryption. So the flits, which are the words of the individual packets of the protocol, are wrapped in an AES GCM stream. Therefore, thanks to the properties of GCM, we have both encryption on the data and integrity protection. So the payload, the user data is completely encrypted and integrity protected. The rest of the fleet's data, basically, for example, the fleet header, is used as an associated data in the GCM stream. Therefore, it is subject to the integrity protection, but it is not encrypted. First, because it does not carry confidential data. And second, because the actual protocol implementation needs this data in clear to be able to work properly. For example, in the case where we have some active switches in between, which should be able to properly route the fleets of the protocol. We have furthermore a CRC check, which obviously is not intended for a security wise integrity protection, but just for reliability. So to avoid errors due to the malfunctions of the device, but not this is obviously not safe against malicious attackers, but we have the GCM integrity protection for that. So we can see here on the right, there is an example scheme of Cxl implementation where we have a host, okay, and a Cxl type 3 devices, which the two of them are connected through their respective Cxl physical ports, okay? And we have the a link level encryption, which is performed in between those. So the data, whenever it transits outside of the boundary of the Cxl device and before it enters, up until it enters the host, it's AES GCM encrypted. So we are completely excluding any kind of attack which is based on the physical access to the link itself. So it seems that we are implementing a sound cryptography, but a question arises. Are we talking to the right device? So if we are the memory, are we talking to the legitimate host? Or conversely, if we are the host, are we talking to a legitimate memory? Because we might be securely talking with the attacker itself. So it is not enough to just guarantee confidentiality, integrity, and replay protection. We need a proof of attestation. We need a proof of determining whether the entity which we are talking about, which we might not have seen before, it is legitimate, and we should communicate safely with that entity. Cxl standard does not impose an authentication mechanism. So any company which is adopting the standard can choose to deploy its own chain of trust, or another example could be trust on first use policy, in which you accept the identity of a memory the first time you encounter it, and subsequently you only accept connections to a memory, and you only accept existing data stored in a memory only if you saw that memory in the past, if you recognize the public key of that memory. But how can we ensure that the device we are talking to isn't already compromised? So even a cryptographic authentication, so an exchange of challenge based on an asymmetric key scheme properly tied to a chain of trust does not protect us from a device which might have its firmware compromised or modified with some malicious component. To that, on that side, basically, what Cxl is preparing in its specification right now. It is not still embedded, but it's in the works inside the consortium, is the integration of the device identity composition engine, which is a specification by the TCG group, which enables a device or a host to generate self-signed certificates, which are tied to the security state of a device. In fact, the DICE works like this. All the software layers which are executed in a device, they are measured, okay, in a hierarchical way, such that the previous layer which gets executed measures the next one and use that hash to derive a cryptographic secret, which is then passed to the other layer. So we leverage the fact that we inherit some information from the previous layer. For example, the bootloader computes a first secret, and it starts from something immutable contained in the device, and then measures the next layer of execution and take that hash, and basically with that hash it computes a symmetric secret which can be used in the end to generate an asymmetric key, which is dependent on the unique set of hashes which were observed up to that point. So thanks to DICE, we are able to obtain a set of public and private key, which are generated every time that we perform the boot, and they won't change. Basically, if ever the firmware does change, for example, as a consequence of a malicious action, we have the guarantee that these keys will change. So the device won't be able to perform an attestation with the same key that it used before if the firmware changes. We have a way to make sure that the attestation mechanism that I've described are properly tied to the Cxl IDE link encryption scheme. And the way the Cxl consortium is planning to do this is to secure the process of exchanging the keys used for IDE. In fact, if we employ the SPDM protocol framework for implementing the Cxl key exchange mechanism, and we employ the keys which are generated through DICE in the SPDM protocol itself, which is let's say something like the embedded version of TLS. So it's a protocol in which we have a challenge mechanism. Therefore, we are able to exchange some ephemeral keys which are provide an embedded attestation proof. So if we, since in Cxl the IDE keys are exchanged in an authenticated SPDM session, we have the guarantee that we are talking with a device which is trustworthy. So putting everything together, we have a protocol stack in which basically we have several actors like the host, or for example the BMC, which might be itself an independent actor in this scenario, which are able to securely talk with a Cxl type 3 device, which are able to request an attestation from that device, for example, demonstrating that its firmware was not tampered with. And as a consequence of that attestation being successful, they can establish a set of ephemeral symmetric keys with that device, which can then be used to perform an AES GCM link encryption between the host and the device, which then in the end will ensure that the physical integrity and confidentiality and replay protection of the data is preserved.